Welcome to Real GMAT Problems, episode 27. Doing real GMAT problems is one of the best ways to make test day easier, so let's talk through a few examples. The problems that we're going to go through are from the 11th edition of the official guide for GMAT review, and you can web search them if you would like to follow along visually. Just so you know, the 11th edition of the official guide is out of print, and that's partly why I'm going through questions from that book, because that way, if you purchase this year's official guide, there shouldn't be any overlap between the questions that we're going to work through here. The official guide contains retired problems that have appeared on past GMAT exams, so these are going to be very similar to what you'll see on your official GMAT. I'll give you a chance to work through the solution on your own if you'd like, and then I'm going to discuss my thoughts on what to take away from each one. I recommend pausing after I read through each problem and trying to solve it, or at the very least, visualize how you would solve it. You might not be able to execute all the steps in your head if you're on the go, but just do your best. If you are in a situation where you can physically write down what you would on test day, that's definitely ideal. Let's go. As we get into some more difficult problems in this series, we may occasionally sprinkle in an easier one to start with as like a warm-up, so I'm going to do that today. If you have feedback or requests about anything that we're doing here, you can reach us anytime at the GMAT strategy on current social channels, or you can email us at contact, C-O-N-T-A-C-T, at thegmatstrategy.com. Let's start with a problem that's a little bit on the lower side of the difficulty spectrum. If you're just starting out, this one might be a little tough, and that's fine. You're here to learn, you're here to improve, and that means you might not get everything right all the time, and that's not necessarily a bad thing, actually. Sometimes you're going to learn more from getting things wrong and making mistakes than you would from getting things correct. I know that's definitely true for me, and that's just part of the learning process. So try to think about it like a workout that feels hard or that you're struggling to complete. Would you feel bad about a workout that felt that way? I mean, obviously, there are certain situations where you would, but most of the time, you'd probably realize that that's actually when the workout is being done properly. So try to cultivate that same mindset here. This is problem number 107. The problem says, what is the smallest integer n? And they make a variable n, the letter n as in nobody, nothing, nowhere. What is the smallest integer n for which 25 to the n power is greater than 5 to the 12th power? I'll read that again. What is the smallest integer n for which 25 to the n power is greater than 5 to the 12th power? Option A is 6. Option B is 7. Option C is 8. Option D is 9. And option E is 10. I recommend pausing to work through this. I'm just going to jump right in so there's no dead air. Obviously related to exponents here. So it's a great skills check and a good execution check. Most of us end up getting this question right, but about 9% of us go for option A as an alpha, which unfortunately is not right. So let's talk about why that happens and how to keep yourself from going down that particular path. First things first, if you feel you don't have a good grasp of exponents, algebra, or inequalities, you'll probably want to work through those basic skills before proceeding. So we've got some math basics episodes on each of those topics linked for you below. Assuming you've got those basic skills in a solid place, though, the best strategic move for most of us in these exponent questions that have like an equation or an inequality in them is to try to make as many of the bases the same as you possibly can. So here you'll notice we've got a base of 25 on the left and a base of 5 on the right, and those are not the same base. But if you think about it, is there a way to make those bases the same? Yes, we can rewrite 25 as 5 squared, or 5 to the second power. And then we would have 5 to the second power in parentheses, that thing, to the n power, and then greater than 5 to the 12th. And that's actually a much better position to be in because we now have the same base in every term of the expression. Now, you don't always need the same base in every term of the expression to make progress through a question with this technique, but in a situation where you can get everything to be the same base, that usually is really, really helpful. And we're going to see that here. If we simplify the exponent on the left, and we're just using an exponent rule, which is when I take a power to another power, I just multiply those two powers together. We would get 5 to the 2n power. 5 to the 2n is greater than 5 to the 12th. And if you have exactly the same base on the left as you have on the right, then you can just ignore the bases. For example, if we had an equation like 2 to the x power equals 2 to the fifth power, 2 to the x equals 2 to the 5, the only way that equation can be true is if x is equal to 5. Similarly, here, the only way that 5 to the 2n power can be greater than 5 to the 12th power is if 2 times n is greater than 12. And because that rule applies so much of the time with so few exceptions, in general, when you have the same base on both sides of an equation or an inequality like this, we can effectively just ignore the bases and focus on the exponents. And if we do that, we would get 2 times n is greater than 12. And that's a much simpler situation to deal with. So that's why that approach is valuable. At that point, we can use algebra to just divide both sides by 2, and we can get n is greater than 6. So what's the minimum value of n that's greater than 6? That's going to be 7 because n has to be an integer. And we know that because the problem told us that. So that's a solid way to get to the right answer here. Of course, that's not the only way to get to the right answer, but it's a great approach. If you aren't familiar with it, it's very worth understanding. And that's option B, as in beta. That's the correct answer. So why are 9% of us going for A? I mean, it's not an overwhelming amount, but as you've heard me talk about, if you've been listening to the series for a while, that's still a pretty hefty percentage. Like if you think about 100 of the brightest business leaders or future business leaders of your generation in a room together, and then 9 of those people pick A here, like it's a little bit surprising, I think. Like that's what I think. Um, and I think if we dig into why are a good number of us picking that, I'm not sure if it all fits into just one mistake. There are a lot of reasons why someone could pick A here instead of B, but my guess is that people do all the math correctly, but accidentally solve the problem as an equation rather than an inequality. I mean, just based on the many, many experiences that I've had with people solving GMAT problems and helping people solve GMAT problems in a variety of settings, that kind of thing just happens. And like myself included, having solved many questions and having struggled with the exam to in just an unbelievable extent. Myself, I have definitely done stuff like that. So it happens. Like sometimes why it happens isn't even that important if we can come up with a good solution. But I do like digging into why it might be happening because I think that can naturally lead you to what is a good way to counteract that, if that makes sense. So just trying to encourage you to think productively about your review process, whether you're getting questions right or wrong. Because at the end of the day, like just doing questions isn't necessarily going to move your score. It's learning from questions that moves your score. And that might sound just like painfully obvious, but I think it is worth remembering and worth reminding ourselves like it's not necessarily about how many problems I complete. It's all about how much skill do I gain from each question that I complete. So um let's just think about like if I wind up with n greater than 6 at the end, that's a really different situation than if I wind up with n equals 6 at the end. Definitely going to make me want to pick A if I have n equals 6 on my page. And that can come from transcribing the problem improperly. I bet a lot of people wind up reading the problem correctly and then just writing incorrectly on their page 25 to the n equals 5 to the 12 as improbable as that might sound given the importance of the exam. Happens all the time. Or a lot of times it happens from just miswriting the math once it's on your paper and you start solving. Like you might transcribe the problem properly, and transcribe just means like I wrote something down from another source. So like I'm looking at the computer screen on test A, I'm like, okay, here's the question. Let me put that on my scratch pad. That's transcribing. But sometimes you transcribe it properly with the inequalities, and then as you're solving it, your brain just kind of goes into an old pattern of making an equation instead of an inequality. Happens all the time. In fact, I've seen people on problems like this write n is greater than 6 and then just pick 6. Like sometimes the kind of fault happens at the end where we just either literally bubble the wrong thing that we didn't mean to bubble, or our brain just like takes a vacation right when we need it most and decides to just make it an equal sign mentally, even though we are literally staring at an inequality on the page. Um, so all of those kinds of things can happen here, and they're all totally understandable mistakes. At the end of the day, I think the fix for all of them is probably pretty straightforward for most of us. There are definitely a wide variety of ways of combating this mistake, but I'll just give you two good habits that I've seen help a lot of people that are like really, really hard to mess up or hard. It would be hard for these to hurt your performance, if that makes sense. Just always write what the question asks. Like it is really, really common to not do that. Again, very understandable. There's a lot of time pressure. Seems like a waste of time. Seems like it's slowing you down. But I found that people who write the question down actually end up finishing questions faster, even if they might be quote unquote like starting the question slower. That's been my experience. And another good habit is just always double checking things you write down from the problem. So after you do your transcription, just looking up at the computer screen and being like, okay, did I get all that properly? Like that's something I do basically 100% of the time, even at my level, having done this for a long time. If I'm doing questions or if I am taking an official GMAT for R&D purposes and I'm actually trying to score high, I'm not just trying to like intentionally get a lower score in order to do like R&D on what's happening. Um, R&D stands for research and development. Sorry, I'm trying to get away from abbreviations and acronyms. I've just realized they're like inherently unclear. But yeah, I guess old habits die hard there. So anyway, sometimes I'll take the exam just to like see what's going on and stay up to date. Um, but if I'm trying to perform and avoid missing questions I know how to do, which is the vast majority of the time, then I will always double check things. I mean, it's just a habit that I've found super simple, super profitable, and it really doesn't take as much time as it usually feels like it takes. There's usually a difference between our like internal feeling of how long something takes and the actual clock time. That's what I've noticed for myself and for tons of people I worked with at least. So not saying you need to do any of this, just making some suggestions, trying to be as helpful as I possibly can. Yes, I mean about 90% of us are getting this question right, so maybe it's not the biggest pain point ever. But clearly a non-trivial number of us are missing it. And so seems like it's worth discussing. And I thought it might be a good little warm up for the rest of the lesson because we're actually going to see those habits that I just mentioned, as simple as they are, be super, super, super helpful on some questions that are going to be just a little bit tougher than this one by the numbers. So uh, why don't we just quick pause there? If there's anything you want to write down or make like a note to self, like send yourself a text or an email, I definitely recommend that if you're on the go. If there's like, oh, I really want to remember this thing, or I want to make a flashcard about something, whether it be an exponent rule or one of the strategy recommendations I've made here, I'd recommend doing that now. Hit a quick pause, and then we'll jump into the next problem. This is problem number 108. The problem says, if x and y are different prime numbers, each greater than 2, which of the following must be true? And there's three statements. Roman numeral 1, or statement 1, is x plus y cannot equal 91. So it's, to be clear, on the screen, it's x plus y does not equal sign. So it's an equal sign with a slash through it. That means does not equal. X plus y does not equal 91. That's Roman numeral 1. Roman numeral 2 is x minus y is an even integer. I'll read this again in a second. Roman numeral 3 is x divided by y is not an integer. I'll start at the top. If x and y are different prime numbers, each greater than 2, which of the following must be true? Roman numeral 1, x plus y does not equal 91. Roman numeral 2, x minus y is an even integer. Roman numeral 3, x over y is not an integer. Option A is 2 only. Option B is 1 and 2 only. Option C is 1 and 3 only. Option D is 2 and 3 only. And option E is 1, 2, and 3. Again, I recommend pausing and attempting your solution, or at least imagining what a good solution might look like. And then when you're ready to proceed, let's pick back up. This one definitely gets a lot of people. Obviously, the content itself is not super complicated, as most of you will know what prime numbers are, what even numbers are, and what integers are. Most of you will know that. But if you are just starting out and this is like one of your first contacts with the GMAT and you want to brush up a little bit on your basic math definitions as they relate to the exam, then just check out our Math Basics episode on definitions, which is linked in the description of this content for you. And that'll get you up to speed, and then feel free to return here when you're ready. So, despite the seemingly basic math content here, 30% of us are getting this one wrong, with 21% of us going for the same wrong answer choice. So it's a heavily concentrated number of misses. Let's try to meet this one head on. Clearly, there's a gap. Let's fill that gap. Let's make sure you're good to go with something like this on test day. Even though this might be like too basic of a place to start, let's for sure make certain we're on the same page with what questions like this are asking. I have noticed there is a surprising amount of confusion about what questions like this are asking. If the question asks must be true, like this one does, that's another way of saying always true, meaning it is true 100% of the time with no exceptions. That's what a must be true question is asking you for. It's asking you for a statement that is true 100% of the time with no exceptions. So what that means is if we can find just one exception to one of these statements, then that means it is not always true. It is not quote unquote must be true, and we're not going to select that one. So the barrier of proof is very, very high on these must be true questions. I have found that certain types of people get pretty confused with the basic premise of that. So just wanted to touch on it briefly. Might be worth making a flashcard or a note to self out of if you're worried about misinterpreting something like that in the future. Usually in questions like this one where we get Roman numerals and basically like three things we either need to prove or disprove, it's a good idea to pick the easiest Roman numeral to deal with first. And sometimes you can make some quick eliminations based on that. So you might have noticed that the answer choices are all different combinations of those Roman numerals. If I can find one of the easier ones to evaluate and potentially prove that it is not always true, then I might be able to eliminate some of the options relatively quickly. That can give me leverage if I need to guess eventually, or I can't figure out one of the other Roman numerals. So just a small tip, but I have found it really helpful. In this question, let me just sketch out how that might look. If I look at Roman numeral 1, it doesn't look too bad, but I am probably going to have to think of some big prime numbers in order to figure out a sum that's close to 91, if it even ends up being possible. So to me personally, that would be feeling a little hard on first glance, and I wouldn't be starting with that one if I could avoid it. So I would look at Roman numeral 2 before I do any like quote unquote math or reasoning beyond what I just said. And to me, that looks a little bit easier because I only have to think about evens and odds. I don't necessarily need to think about prime numbers that might add up to 91 because those are going to be some relatively large prime numbers for most of us. Most of us are going to be familiar with the first few prime numbers, but like you probably haven't memorized like the prime numbers in the 40s or the 50s or the 60s. That would be unusual. So hence potentially going for statement 2 first. Since the vast majority of prime numbers are odd, I might want to start by attacking Roman numeral 2 first rather than the first one for the reasons I just explained. So here we know that the prime numbers we're dealing with are greater than 2. So they actually have to be odd because 2 is the only even prime number. So if we are dealing with prime numbers that are greater than 2, they must be odd. And all I have to do is subtract a few odd numbers from each other to see that the result will always be even. Conversely, of course, you can memorize that the sum or difference of any two odd integers, excuse me, will always be even. Both approaches work if you want to do the guess and test thing, or if you want to memorize it, or both. That's cool. Both are good, but you will want some method of figuring out how sums and differences are either odd or even. It's a concept that does come up quite a bit on the exam. So personally, I like the idea of starting with Roman numeral 2 and just putting Roman numeral 1 to the side because every prime number greater than 2 is for sure odd, and any odd number minus any other odd number is always even. Roman numeral 2 must be true 100% of the time, aka it is always true. And that's great news because once I know that, I can eliminate the answer options that don't include Roman numeral 2. like option C. So let's go ahead and eliminate option C as in Charlie, which you might recall is 1 and 3 only. And we know that that's not the answer here because we just proved that Roman numeral 2 works 100% of the time. So, yeah, I mean, is that a game changer eliminating C based on Roman numeral 2? Maybe not, but is it helpful? Yeah. Does it make the problem a little more approachable? I think so. And I think it increases the odds of guessing and maybe even gets you enough momentum and understanding of the context of the problem to figure out some of the more difficult Roman numerals a little bit easier. So that's my advice there. At that point, I would check out Roman numeral 3 and see if that's going to be easier to deal with than 1. If it's not, I'll just go back to 1 and deal with it. But if it is easier, I would be happy about that. And that says x over y is not an integer. And personally, I think that is also a little easier to think through versus Roman numeral 1 because I don't have to think about any big prime numbers. I can just think about like 3 over 5, 7 over 3, 11 over 5, some of the prime numbers I'm probably more familiar with. And I would realize, hopefully, that because prime numbers are only divisible by 1 in themselves, there's no way that they could be divisible by another prime number, a different prime number. And that's partly why it's so important that the problem mentions that x and y are quote unquote different prime numbers. That is super, super, super important. Without that constraint, 3 might not always be true because if x is 7 and y is 7, then they're both technically prime, but are obviously going to create an integer when divided by each other because 7 over 7 is 1. But because we are told that x and y are different, we know for sure that 3, Roman numeral 3, will always be true. It will for sure be true that if I divide a prime number greater than 2 by a different prime number greater than 2, it will not be an integer. So we can now eliminate any options that do not include 3 because we just proved that 3 is always true. So we can eliminate A, which says 2 only, and we can eliminate B, which says 1 and 2 only. So that's kind of nice. That's kind of nice. That gets us down to D and E, which means we do need to go figure out if 1 is true all the time to get 100% certainty. But even if I couldn't ever figure out number 1 or I was really time constrained, I've got a 50-50 shot, which is a lot better than a 20% shot, which would have been what I had with a random guess. So good news is if we put our thinking caps on a little bit, 1 isn't too bad to deal with, but I do think it's the toughest one personally, and we're going to see that when we look at the wrong answer distribution in a second. So it is a little easy to get lost. So what I like to do when I have to deal with larger numbers or like long lists of numbers is just picking some kind of systematic way to list them out. Now, I know this might sound just like crazy or like comically basic, but I promise it is a super high leverage technique. And that's always what I'm trying to give you all here in this like public format where I don't have all the context on your personal situation is give you the stuff that's the easiest to implement that will have the biggest positive impact. And I think that's how we're going to basically get the main objective of what we want to happen here to happen. Um, so this like listing in a systematic way is a super, super simple thing. But I think you will like it if you learn to use it well. So let's talk about how to use it well. A lot of people don't do the listing thing because it just seems like it's going to take forever. And that's a totally legitimate concern, by the way. Like what happens if there's like 50 different possibilities I have to list out? Like that's not going to be practical. But the kind of the inside scoop with that is you are almost certainly not going to have to count them all because you will generally start to see some kind of pattern if you're systematic in the way you list numbers out. So let me try to show you what I mean rather than just describing it. Let's start with x being 3 since that's the smallest prime number greater than 2 and the minimum value that we can use. And let's make y equal to 5, which is the next smallest prime possible given the constraints of the problem, which is that they're larger than 2 and they're different. So what I'm doing here is I'm like, okay, like prime numbers in the 70s, 80s, like 90s, that's going to be kind of tough. I got to see if they sum up to 91. So, I might have to do some stuff in like a 40 plus a 50-ish, something like that. And I might not be super comfortable with those primes. If you've memorized all your primes up to 100, then, this question's probably going to be no big deal. But that's not most of us. And even if we do try to memorize it, sometimes it's not there when we need it on test day. So this listing out approach can be helpful. And what I'm doing my like quote unquote systematic way is also comically basic. It's just starting as small as I can and then moving up one increment at a time. And usually, if you have like some kind of really simple systematic way of listing things, you will see the pattern. So let's try that. So if x is 3, y is 5, the sum of 3 and 5 is 8. Okay, that's not helping me much. Let me get a few more things down. So then I'll go to the next smallest pair of numbers I could do, which would be 5 and 7. 5 plus 7 is 12. I would write that down under 3 plus 5 equals 8. Then I would go to the next one, which is 7 plus 11. That's 18. Then I would go 11 plus 13. That's 24. Again, if you look at those and you think about like what do all these sums have in common, hopefully you would start to see the pattern. It's okay if you don't. But because we're always adding two primes and those two primes are always odd because they're bigger than 2 and 2 is the only even prime number, that means we're always going to get an even result. So interestingly, I was a little bit wrong about Roman numeral 1, and I don't actually have to think about super big primes at all. I just have to recognize, like I did with Roman numeral 2, that the sum of two odd numbers is always even. But I do think it's a little bit harder to see that and think through it in that lens with 1 versus 2, where the 2 literally mentions even versus odd, whereas 1 is just like, wait a minute, do I have to like think about 89 plus 2 or something like that? You know, like is 89 even prime? Like I would prefer not to go down that rabbit hole at the beginning of a problem. So many of you might have been able to see what I was just talking about from the beginning, and if that's true, that's amazing. That's awesome. That's great news. You're probably not going to struggle with this kind of question. But if you're like me and you did not see that from the beginning, then using this like really simple approach of just listing things out systematically, if you're like, how am I going to count up like 100 different pairs of prime numbers? Just as soon as you have that thought, be like, well, let me just list out like the first 5. Let me see if I can find a pattern there. Okay. So again, my system was just smallest possible different prime values. And I just kept stacking the smallest, the next smallest, the next smallest. And that can be surprisingly helpful. It's not a silver bullet, meaning it's not necessarily going to fix every problem that you have. And you might not see the pattern 100% of the time, but it's usually a lot better than nothing or just staring at the problem and hoping for the best, which is definitely what happens in a lot of these situations. Uh, yeah. So anyway, the listing and counting thing kind of allowed me to see the theory behind the numbers in the Roman numeral 1, which is like, oh, right, of course they're all even. It's all odd numbers, all sums of odd numbers. So that's always nice when you can get that moment to click. So that leads us to our correct answer, which is option E, as in echo. All 3 of those Roman numerals must be true. Let's dig in a little bit and think about what we can learn from a question like this. There are likely some specific notes to self that you can make, including maybe you got this totally right. Maybe you're all good with questions like this. That's cool. But for a lot of us, there's probably going to be some kind of changes we're going to want to make in our thinking and our process. And apparently that happens about 70% of the time, which is the hit rate on this question for us as a group. So the first thing that comes to mind here, sorry, 30% of us would want to change what we're doing. 70% of us get the question right. But still, I think that's surprisingly low. You know, I mean, you go back to the analogy, 100 people in a room, future business leaders, 30 of them are missing this question. Seems a little too high. Let's try to fix that. So first thing that comes to mind that might be a good note to self here is if you weren't able to wrap your mind around number 1, the listing things out approach, as simple as it is, usually helps. Just remember to have some kind of system if you're counting from high to low. Keep your numbers as big as possible. If you're counting from low to high, like I was, keep them as small as possible. Some kind of framework for the numbers you're listing out rather than just listing random pairs. Listing things randomly usually doesn't help. Second thing that comes to mind is 21% of us are picking D, which is the answer that says 2 and 3 only, but not 1. And I think that points to a couple potential issues. The first is maybe people don't realize they can list and find a pattern. So like what I was talking about, like just thinking like, oh man, that's going to take forever. Probably not true. Like, let me just guess, you know, and move on. Like that's understandable if you're tight on time, but hopefully we just resolved that belief that it's like not possible to count it up. Yes, it's probably not practical to count every single pair, but if you just count the first few pairs, usually you'll notice a pattern. The next is I wonder if people are forgetting the numbers have to be larger than 2. That was my second thought there as to why people might be thinking 1 is not always true or doesn't have to be true. For example, I could definitely see people not writing that constraint or like writing it down and just forgetting it as they move through the problem, and then thinking about something like 2 plus 89. Um, 2 is a prime number, 89 is also a prime number, and then thinking, oh, cool, that's exactly 91. So x plus y could be 91. So, obviously that doesn't have to be true. Like, in a way, like some people are a little too smart with that, and they're thinking like 2 plus 89. Um, so that's one thing that could be happening there. We talked earlier in our warm-up problem about writing things down and double checking your constraints. That's probably a good fix for that one if that happened to you. Another possibility is simply thinking that because 2 is even and other prime numbers are odd, that you'd be able to get an odd result from adding them. So like maybe you're not thinking about 89 as a prime number, but you're thinking like, oh, even plus odd, one of the prime numbers could be 2, so therefore like I probably could get 91 somewhere in there. Either way, those paths basically involve forgetting the constraint, which is a very avoidable mistake, but also one that happens a lot, as you might imagine. A lot of time pressure, a lot of stress, a lot of just general pressure attached to these exams, a lot on the line, if you will. And again, usually that's just fixed by writing down the constraints at the start of every question, which is generally a great idea, or always double checking your work after you write things down and before you select your final answer. So even though by the numbers, this question is like a much lower hit rate than the first one, those same habits tend to scale really, really well to a wide variety of questions. There might be other reasons why people pick D. I can definitely see people looking at the does not equal sign and thinking it's actually an equal sign, similar to like switching the inequality to an equal sign in the previous problem. Kind of thing happens all the time. You would think like, I don't know, you would think like it wouldn't be that big of a deal, but yeah, just all kinds of crazy stuff happens to us during these exams. Sometimes we're going too fast. Sometimes we're just misinterpreting it without realizing it. Like our brain just sees an equal sign, even though it says not equals. That can happen. So there's plenty of interesting pitfalls to speculate on here and to study and to think about and to try to engineer your process to like solve those problems before they happen. That's really one of the main things I'm trying to help you with in this series. So with all that being said, I would recommend pausing and just asking yourself if I could only remember one thing from thinking through this problem, what would it be? And just make that note. When you're ready, let's try another one together. This is problem 110. Problem says, if candy bars that regularly sell for 40 cents each are on sale at 2 for 75 cents, what is the percent reduction in the price of two such candy bars purchased at their sale price? I'll read that again. If candy bars that regularly sell for 40 cents each are on sale at 2 for 75 cents, what is the percent reduction in the price of two such candy bars purchased at the sale price? Option A is 2.5%. Option B is 6.25%. Option C is 6.2%. Option D is 8%. And option E is 12.5%. And the answers are written as mixed numbers like that. If you're not familiar with mixed numbers, we got a whole GMAT Math Basics episodes on fractions linked for you below. Again, recommend pausing, giving this one a shot, and then we'll dive in when you're ready. I thought this was a really interesting parallel to the previous question and maybe even the first one we did also, since again, the mathematical concepts here aren't super advanced. We've got some percents, we've got some decimals, and that's pretty much it. And yet, 23% of us are missing this one. I think that seems a little high. So great example of how the exam can take some simple concepts and construct a problem that can be really tough and tricky, just like the previous one. So let's break this one down. Once again, let's make sure you're ready for something like this on test day. So we actually talked about a nice strategy for questions like this in our previous episode in this series. So please check that out if you want a bit more practice with this kind of situation. But what I recommended there is something called the percent change formula. It's definitely worth memorizing it if you haven't already. And the formula is just new value minus old value, that difference, new value minus old value, that whole thing divided by the old value. and then that whole fraction times 100. And that's always going to equal your percent change. So again, it's new minus old over old times 100 equals percent change. I recommended it last week because even though there are potentially simpler ways to create equations here, I've noticed over the many years that I've been doing this that a lot of people get mixed up, they get turned around, or they just straight up get confused when they're trying to do the real world logic and the math and trying to get those things to add up. Even like super intelligent, really accomplished people end up making that mistake, and it's just kind of like an unnecessary pain. So we'll try to get rid of it here. What I like about the percent change formula is that it helps bridge the gap between the real world and the math world. So, for example, just having a formula that by definition distinguishes between a new value and an old value as part of the formula is a really nice bridge to the real world. Most of us are going to be able to look at a problem like this, put our thinking cap on, and be like, okay, this is probably the new one, and this is probably the old one. And that automatically starts to situate the math part in the right place. So if you thought about it for a moment, odds are you would be able to determine here that the old value is the price before the discount, and that the new value is likely the price after the discounts. Very high odds that you're going to be able to figure that out because that's how things typically work in the real world. Now, for sure, I imagine some of us are getting confused about that on this problem, and the incorrect answer distribution definitely seems to bear that out. But I would say for the majority of us, that's going to be simpler than trying to think through whether a discounted price should be like X or Y or on which side of an equation that should go on. Now, for sure, some of you are going to be able to go straight to an equation with this with ease. And if that's you, that's amazing. There's no need to change anything that's already working. For most of us, though, I think the percent change formula is the way to go. So I'm going to talk through exactly what that would look like and then show you how I think that helps prevent some of the apparent pitfalls of this particular question. So let's start with what the question asks, which is always important, but particularly important in this problem. It asks for the percent reduction. That's a good cue that you're going to want to use the percent change formula in the price of 2 such candy bars. And that's super important because it's fairly clear from the incorrect answer distribution that quite a few of us are doing the math for just one candy bar, which we definitely don't want that because that's going to get us the wrong answer. Assuming we did get the question understood properly, though, we can now put some values in for the new value and the old value in the percent change formula and get our answer. So the new value is given to us, says it's on sale, 2 for 75 cents. And because sales prices are generally a function of the original price, it's safe to assume that sale prices are always new values with percent change formulas. And our old value might appear to be 40 cents on first glance, but that's true for only one candy bar. So because we want to do the price reduction for 2 candy bars, we need to double that. And the old price would be 80 cents for 2. New price of 2 on sale is 75. So 80 cents is going to be our old value. So our formula might look something like 0.75 minus 0.8. That whole thing divided by 0.8, and then that whole fraction times 100. If we do the math there, we would get negative 0.05 on the top. That's 0.75 minus 0.80. Negative 0.05 on top, and then on the bottom we'd have 0.8. And then, of course, we have times 100. Now, I'd prefer not to deal with decimals inside of a fraction. That's a situation that's very, very error prone for a lot of us. So I'm going to make an optional move here, but one that I do find helpful on a consistent basis. And I'm going to multiply the top and the bottom of the fraction by 100. Since I'm multiplying by 100 over 100, I'm really only multiplying by 1. So I'm not actually changing the value of the fraction. I'm just changing the way that it looks. I'm making it a little easier to operate on. So if you'd like some more specific and a little bit more basic advice about how to handle fractions well, since we don't get a calculator on the quant section, we've got a math basics episode linked for you below. That's going to walk you through that. Now, making that move would get me negative 5 over 80 times 100, and that's just going to help me cross cancel a little bit more easily. If you don't mind the decimals in the fraction, that's totally cool, but I like to get rid of them. So I've got negative 5 over 80 times 100. I like to write it as 100 over 1. I talked through why I like to do that last week. Just is less error prone, I've found, and it allows me to visually cancel out things from the numerator and the denominator. So first I'm going to take a 10 out of 80 and 100 to get negative 5 over 8 times 10 over 1. That simplifies things a bit. And then I'm going to take a 2 out of 8 and a 2 out of 10 to get negative 5 over 4 times 5 over 1. At that point, I'm probably just going to multiply straight across the top and get negative 25 over 4. From here, I can do long division. No problem with that. You've heard me do that a lot in the past. going to give you a slightly different take here where I could like cut 25 in half to get 12.5 and then cut 4 in half on the bottom and get 2. It's almost like I'm canceling a 2 out of there, a little bit more advanced move, but it can work. And then I can basically do 12.5 divided by 2, and that's going to be 6.25. If you're not comfortable with that, just do the long division. Now, tons of ways to handle that math, but I like to try to explain some of my thinking and reasoning behind how I execute. So you can see, number one, that not everyone needs to do things the same way to be successful on the exam. And number two, it's okay to do math that's not like a super genius way of doing the math and still get really great results. I think sometimes trying to do that like really slick, quick approach to computation in the interest of saving time, which I've seen a lot of people recommend out there, I have found that that usually makes things harder, not easier for people. Just saying. Not trying to insult anyone's approach to the exam. I'm just telling you my experience, which is extensive. I've noticed a lot of people can get just confused when they're trying to do that, and they'll end up missing a problem that they should have gotten right just because of like rushing the calculation at the end, which is it's really just not a good trade. Like picking up 5 extra seconds for like a 3x larger risk that you're going to miss a question you actually knew how to do. I really don't see how the numbers work out there long term. So that's my take. Hope it helps. At any rate, if we execute our percent change formula properly, we would arrive at our correct answer of 6.25%, which is option B, as in beta. Let's briefly touch on why it's okay that we got a negative value there. Technically, we got negative 6.25. Anytime there's a percent decrease and you're using the percent change formula, you're going to get a negative value. And that's because the new value is less than the old value when things are decreasing. But note that this problem says percent reduction. And that word reduction is important. If I have a negative 6.25% change, that's the same as a positive 6.25% reduction. Like the reduction is kind of like takes the place of the negative sign. So that's why the answer choices themselves are positive. So just to make sure that's totally clear, if the problem asks for a percent decrease, you should expect a negative value in the percent change formula itself. But the correct answer will be expressed as a positive percentage because a positive decrease is the same as a negative number. Now, if you think about it, what would a negative decrease be? That's an increase. So we don't want that here. It's a little weird, but if you do a few practice problems with percent change, like the one we did last episode, then I think it should make good sense. But you're always free to reach out if it doesn't, and we're happy to help. So let's talk about a few incorrect answers here that are really, really prevalent. So if the first one is option C, which is 6.2/3%, and it looks like about 11% of us are going for that one. Just think about for a second, any idea why someone might get an answer that's just a little bit too big? That one's just a little bit larger than the correct answer. Why might that happen? It's worth considering. My guess is that a lot of people mix up the old value and the new value. So they're using the right formula, but they're reversing the 75 and the 80. Because if I do 80 minus 75 or 0.8 minus 0.75 over 0.75, or 80 minus 75 over 75, like I just switched the new and the old values, then I am going to get 6.2/3 as my answer. So let's talk about how to prevent that, because nobody wants that. There's definitely a lot of promising ways, but the easiest that I've seen to implement is just a quick double check of any discounts or price raises in percent change questions specifically. So going a little narrower than my broader takeaways before. So anytime you're doing percent change, just double check, is this a reduction or a price increase that I'm doing here? Like last week we did an increase with a tax. This week we're doing an increase with a sale. Sorry, a decrease with a sale. So two sides of a similar coin. And right after you set up your formula, just ask yourself if your new value comes after the change. And if that's the case, everything's good. So you're like, okay, I'm doing some kind of percent change here. Is my new value the thing that is the result of the change, or is my new value the thing that the change is being done upon? Because if your old value is the one that occurs after the change, like having 0.75 in the denominator, then you've got a problem. And you're probably about to get the question wrong. So you're going to want to change your setup in that kind of situation. So just a quick double check. Am I increasing or decreasing something? And then what am I increasing or decreasing? The thing that I am increasing or decreasing should be the old value. The result of that increase or decrease should be the new value. I know that sounds just like potentially painfully obvious right now, but when you're under time pressure, all kinds of crazy stuff can happen that you're not intending. And so it's good to have a little bit of insurance there. Another interesting and popular incorrect answer, which is E, is 12.5%. We actually already touched on this a little bit earlier, but I wanted to highlight it one more time since that's a slightly different type of mistake in my opinion. So think about how might someone get something that's double the correct answer, right? Correct answer is 6.25. This answer is 12.5. Why might that happen? Couple different ways, but I think probably the main way is if you misinterpret the question and you do the 5-cent discount on one candy bar instead of the two candy bars that the problem actually asks about. So if I do that, I would end up with um, 75 minus 80 over 40, or I might just do 5 over 40 or 0.05 over zero point 0.4. Like if I skip a few steps in my head, that's really, really common. And that's the discounted price over the old price of one candy bar. So kind of like your heart is in the right place with the formula there, but just the wrong thing gets put into the old value. So that would get you exactly 12.5%. So let's prevent that. A quick double check would certainly help there. So not discounting the previous tip I gave, but this one could also be solved by simply writing down what's given and asked clearly before you begin trying to solve the problem. So I've talked about this just a ton in the past because it's so widely applicable. It's so simple, and yet it's just so, so powerful. And a lot of times it just doesn't seem like it's going to be all that beneficial. Writing what's given and asked 100% of the time. I think a lot of people just resist it because it takes time and energy. But again, it's the clock time. If you actually timed how long it takes you to write things down versus the benefit you get from writing things down, I think you will find that that's a very, very good trade, especially if you scale out the numbers, 10, 20 years. So both of those adjustments are highly recommended if you missed this question or you're concerned that you might miss questions like this in the future. And that's three. So let's go ahead and just pause there. As always, if you have questions or feedback about any of this material, feel free to reach out to us. We love hearing from all of you. We are at the GMAT Strategy on current social channels, and you can email us contact@thegmatstrategy.com. And we definitely look forward to hearing from you and helping as much as we can. That's why we're here. We're here to help. If you want more tips and strategies for optimizing your performance on the exam, please head to our website, thegmatstrategy.com, which is linked in the description of this content, and check out our free video on how you can reach your dream GMAT score in half the normal time. In the meantime, this is a regular show, so please subscribe and please stay positive and stay consistent with your studies. Talk to you soon.